In 1965, two Bell Labs engineers named Penzias and Robert Wilson were trying to eliminate a persistent hiss from their radio antenna in New Jersey. They checked everything. They removed pigeons nesting in the antenna and cleaned out the droppings. They checked every connection and every component. The hiss remained, perfectly uniform from every direction in the sky, day and night, summer and winter. They had no idea what it was. A few miles away at Princeton, a team of physicists was frantically building a detector to search for exactly this signal, a faint glow of radiation left over from the birth of the universe. When the two groups connected, it became clear that Penzias and Wilson had stumbled onto the most important discovery in the history of cosmology. They had detected the afterglow of the Big Bang itself, still washing over everything 14 billion years later, and they won the Nobel Prize for finding it by accident while cleaning bird droppings out of a telescope. That accidental discovery confirmed something that most scientists at the time found deeply uncomfortable. The universe had a beginning, not just a beginning in the sense of things rearranging themselves, a genuine beginning where everything, space, time, matter, and energy came into existence from an unimaginably hot, dense state. The Big Bang theory, which had been proposed decades earlier and dismissed by many as absurd, was suddenly on the strongest possible observational footing, and the century of research that followed that pigeon-fouled antenna has transformed our understanding of where we came from, what the universe is made of, and what its ultimate fate will be. The story begins not with an explosion, but with mathematics. In 1915, Einstein published General Relativity, his revolutionary theory of gravity that described the universe as a four-dimensional fabric of space-time that bends and curves in response to mass and energy. Einstein himself immediately recognized something troubling about his equations. They didn't allow for a static universe. The mathematics insisted that the universe had to be either expanding or contracting. Einstein found this so philosophically unacceptable that he added an extra term to his equations, a cosmological constant, a kind of repulsive force that would counterbalance gravity and keep the universe eternal and unchanging. He called it his greatest blunder later in life, and he was right in more ways than he knew. While Einstein was doctoring his equations to maintain a static universe, a Russian mathematician named Alexander Friedmann was solving those same equations honestly without the cosmological constant patch. In 1922, Friedmann showed that Einstein's original equations naturally described an expanding universe that had begun from a single point of infinite density. He wasn't making a physical claim, he was just following the mathematics. Friedmann died of typhoid fever in 1925, largely unrecognized for what he'd found. 5 years later, a Belgian Catholic priest named Georges Lemaître independently derived the same expanding universe solutions and went further. He proposed that if the universe was expanding, you could run the clock backward. Everything would get closer together. Compress it far enough back in time, and you'd reach what he called the primeval atom, a single incredibly dense point from which everything emerged. Lemaître was proposing a cosmic origin story rooted in physics rather than theology, which was unusual given his religious background. He insisted on keeping the two completely separate. The church didn't tell him what physics to do, and physics didn't tell him what to believe about God. The key observational breakthrough came from Edwin Hubble. In the 1920s, the dominant view was that the Milky Way was the entire universe. Fuzzy patches of light in the sky, called nebulae, were thought to be gas clouds within our galaxy. Hubble proved this wrong by measuring the distance to some of these nebulae using a particular type of star called a Cepheid variable. Cepheids pulsate with a period directly related to their luminosity. By measuring the period, you know the true brightness. By comparing that to the apparent brightness as seen from Earth, you can calculate the distance. What Hubble found shattered the old picture. These nebulae were galaxies in their own right, millions of light years away, far outside the Milky Way. Then in 1929, Hubble published a result that changed cosmology forever. He had measured the velocities of dozens of galaxies by analyzing the Doppler shift of their light, the same effect that makes an approaching ambulance sound higher pitched and a receding one lower pitched. Almost all the galaxies were moving away from us. And crucially, the farther away a galaxy was, the faster it was receding. The relationship was linear and elegant. Double the distance, double the recession speed. This was Hubble's law, and it was the direct observational signature of an expanding universe. Space itself was stretching, carrying galaxies along with it, like raisins in rising bread dough. The expanding universe was now observationally established, but not everyone welcomed the logical implication. If everything was flying apart now, everything must have been closer together in the past. Far enough back, everything must have been in essentially the same place. The British astronomer Fred Hoyle found this idea so objectionable that he coined the term Big Bang during a BBC radio broadcast in 1949, intending it as mockery. He spent the rest of his career advocating for an alternative called the steady-state theory, which proposed that matter was continuously created to fill the gaps as the universe expanded, maintaining an eternal, unchanging appearance with no beginning and no end. It was an elegant theory, and it was wrong. Hoyle's mockery backfired because the name was vivid and stuck. But more importantly, scientists began working out what the early universe would actually look like if the Big Bang theory was correct. The key figures here were George Gamow, Ralph Alpher, and Robert Herman working in the late 1940s. They reasoned that if the universe began in an extremely hot, dense state, the early universe would have been filled with a plasma of protons, neutrons, electrons, and photons, all at enormous temperatures. As it expanded and cooled, nuclear reactions would have occurred, fusing some of the hydrogen into helium and trace amounts of other light elements. They calculated the predicted abundances and found that the universe should be about 75% hydrogen and 25% helium by mass, with tiny traces of deuterium, helium-3, and lithium. This prediction of primordial nucleosynthesis was extraordinary because it could be tested. Astronomers could measure the composition of the oldest, most pristine stars and clouds of gas in the universe. If the Big Bang theory was right, you'd find the same ratio everywhere you looked. If the steady-state theory was right, the composition would depend on when and where the gas was created. Decades of measurements confirmed the Big Bang prediction to remarkable precision. The universe really is about 75% hydrogen and 25% helium everywhere you look in the oldest material. This chemical fingerprint of the early universe was strong evidence that the Big Bang actually happened, gamma, alpha, and Hermann also predicted that the hot radiation from the early universe should still be around today, cooled by the expansion of the universe to a temperature just a few degrees above absolute zero. They predicted a faint microwave glow filling all of space uniformly. This was the prediction that Penzias and Wilson unknowingly confirmed in 1965 when they found their mysterious hiss. The cosmic microwave background radiation, as it's called, is the oldest light in the universe, released about 380 zoozoon years after the Big Bang, when the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms. Before that moment, the universe was opaque to light. After that moment, photons could travel freely. The cosmic microwave background is a snapshot of the universe at that earliest visible moment, and it contains an enormous amount of information about what the universe was like at its beginning. The detection of the cosmic microwave background effectively ended the debate between the Big Bang and steady-state theories. The steady-state theory couldn't explain why there was a uniform radiation filling all of space at just the right temperature. The Big Bang theory predicted it directly. Most cosmologists accepted the Big Bang. Fred Hoyle, to his credit, continued working and actually made some of the most important contributions to understanding how elements heavier than helium were made in stars, work that earned the 1983 Nobel Prize for one of his collaborators, William Fowler, though Hoyle himself was controversially left out. The 1970s and 1980s saw Big Bang cosmology mature from a rough sketch into a detailed quantitative science. Increasingly precise measurements of the cosmic microwave background confirmed that it was almost perfectly uniform in temperature, about 7 degrees above absolute zero in every direction. But almost perfectly uniform is not perfectly uniform, and the small deviations from perfect uniformity turned out to contain the entire history of the universe. Here's the problem that emerged in those years. If the early universe was perfectly smooth and uniform, how did structure form? How did galaxies, stars, and planets emerge from a featureless hot gas? You need some initial irregularities, some places where the density was slightly higher than average, for gravity to grab onto and amplify over billions of years. Those slight overdensities would attract more and more material, growing into the galaxies and galaxy clusters we see today. But where did those initial irregularities come from? Nobody knew, and it was a serious problem for the theory. The answer came from an unexpected direction. In 1980, Alan Guth at MIT proposed cosmic inflation, one of the most radical and important ideas in the history of cosmology. Guth was trying to solve several problems that plagued the standard Big Bang theory at the time. One was the horizon problem. The cosmic microwave background is the same temperature in every direction to 1 part in 100,000. But regions of the sky on opposite sides of us were never in contact with each other in the standard Big Bang model. Light from one side couldn't have reached the other side in the time available. So how did they come to be at the same temperature? It's like two people in completely separate rooms who've never communicated, somehow producing identical sculptures without any coordination. Another problem was the flatness problem. Measurements showed that the universe was remarkably close to geometrically flat, meaning its spatial geometry was neither positively curved like a sphere nor negatively curved like a saddle, but flat like a sheet of paper. In the standard Big Bang model, this flatness is extraordinarily sensitive to initial conditions. If the density at the beginning deviated from the critical value by even a tiny amount, the universe would have either collapsed back on itself within a fraction of a second or expanded so fast that no structure could have ever formed. The fact that we exist means the initial conditions were tuned to extraordinary precision. This seemed deeply suspicious, like a pencil balanced perfectly on its tip, with no explanation for how it got there. Guth's inflation theory solved both problems simultaneously. He proposed that in a tiny fraction of a second after the Big Bang, perhaps from 10 to the negative 36 seconds to 10 to the negative 32 seconds after the beginning, the universe underwent a period of exponential expansion, growing by a factor of at least 10 to the 26th in an almost incomprehensibly short time. During this inflation, a region that was small enough to have been in thermal equilibrium was stretched to encompass our entire observable universe. That's why everything looks the same temperature. It all came from the same tiny region that had time to reach equilibrium before inflation began. The flatness problem is solved because any curvature in the pre-inflation universe would have been stretched completely flat by the enormous expansion, the same way a tiny region of a balloon surface looks flat when the balloon is inflated to an enormous size. The universe looks flat because inflation made it flat. But the most remarkable prediction of inflation was what it said about the quantum nature of the early universe. At the quantum level, the vacuum is never truly empty. It's constantly fluctuating, with random quantum variations in the density of energy appearing and disappearing. During inflation, these quantum fluctuations were stretched to cosmic scales. Variations that began as subatomic quantum noise were inflated to the size of what would become galaxy clusters. These stretched fluctuations became the seeds of all structure in the universe. Every galaxy, every star, every planet, including Earth and everything on it, traces its origin to quantum fluctuations that occurred in the first fraction of a second of the universe's existence. This connection between quantum mechanics and cosmic structure is one of the most mind-bending results in all of science. The galaxies we see in the night sky grew from quantum noise. The specific pattern of that inflation-stretched noise has a characteristic mathematical form called nearly scale invariant, meaning fluctuations have roughly the same amplitude on all length scales. This prediction matches what we observe in the cosmic microwave background and in the large-scale distribution of galaxies with remarkable precision. The seeds of all cosmic structure really do look exactly like inflated quantum noise. The cosmic microwave background became the primary tool for precision cosmology in the following decades. In 1992, NASA's COBE satellite made the first detailed map of the tiny temperature variations in the cosmic microwave background. The variations were there, at the level of 1 part in 100,000, exactly as predicted by inflation. The COBE team leader George Smoot described seeing the results as like seeing the face of God. The hyperbole was understandable. They had seen the pattern from which all cosmic structure grew. The Nobel Prize followed in 2006. But COBE was just the beginning of an extraordinary progression of increasingly precise measurements. In 2001, the WMAP satellite produced a dramatically better map of the microwave background, resolving the temperature fluctuations with sufficient detail to measure the geometry, composition, and age of the universe from a single dataset. Then in 2013, the Planck satellite produced the most detailed map yet, with enough precision to measure fundamental cosmological parameters to better than 1% accuracy in some cases. What emerged from these maps was the standard cosmological model, a precise quantitative description of the universe from its beginning to today. The standard model of cosmology, called lambda CDM after the cosmological constant and cold dark matter, describes a universe that is 13.8 billion years old, geometrically flat, and composed of roughly 5% ordinary matter, the protons, neutrons, and electrons that make up stars and planets, and people 27% dark matter, a mysterious invisible substance that doesn't interact with light but does exert gravity, and 68% dark energy, an even more mysterious component that causes the expansion of the universe to accelerate. These percentages are known with considerable precision from multiple independent measurements. The universe is mostly made of things we don't understand at a fundamental level. Ordinary matter, everything we can see and touch and measure directly, is a minor component of the total. Dark matter deserves extended attention because it's so central to modern cosmology and yet so poorly understood at a fundamental level. The first strong evidence for dark matter came in the 1930s from the Swiss astronomer Fritz Zwicky, who measured the velocities of galaxies in the Coma cluster and found they were moving far too fast to be held together by the gravity of the visible matter alone. The clusters should have flown apart long ago if only visible matter provided the gravitational glue. Zwicky concluded there must be additional invisible matter. He called it dark matter. He was largely ignored for decades. The situation changed dramatically in the 1970s when Vera Rubin and Kent Ford measured the rotation speeds of individual spiral galaxies with great care and found something equally puzzling. Stars at the outer edges of galaxies were orbiting at roughly the same speed as stars closer to the center. In a normal system where most of the mass is concentrated at the center, like the solar system, objects farther out orbit more slowly. Mercury moves much faster than Neptune. Jupiter moves faster than Saturn. The planets follow this pattern precisely because most of the solar system's mass is in the Sun at the center. But galaxies don't follow this pattern at all. The rotation curves are flat all the way out to the edge of the visible disk and beyond. This implies that galaxies are embedded in enormous halos of invisible matter extending far beyond the visible disk of stars and gas, providing extra gravitational pull that keeps the outer regions orbiting fast. The mass enclosed within any given radius keeps increasing even where there are no more visible stars, exactly as you'd expect if an invisible halo surrounded the galaxy. Rubin's measurements were precise and careful and could not be explained away by any known physics. Dark matter became accepted not because anyone understood what it was, but because the observational evidence was overwhelming and consistent across many different types of observations. We could see dark matter's gravitational effects in many places. Galaxy clusters bent light from background galaxies more than visible matter could explain. A phenomenon called gravitational lensing where the gravity of massive objects curves the path of light passing near them. In 2006, the bullet cluster observation became one of the most dramatic demonstrations of dark matter's existence. Two galaxy clusters had collided, and the hot gas from each cluster had interacted and slowed down, piling up in the middle. But measurements of the gravitational lensing showed that most of the mass had passed right through the collision unimpeded, separated from the gas. The only explanation was that the bulk of the mass was in a form that didn't interact with ordinary matter at all, exactly what dark matter predicts. The large-scale structure of the universe, the cosmic web of galaxy filaments and voids, matched simulations that included dark matter beautifully but failed badly in simulations without it. The acoustic peaks in the cosmic microwave background had heights that required the specific ratio of ordinary matter to dark matter seen in the standard model. Dark matter was required by multiple completely independent observations. We just had no idea what it was, and we still don't. The leading candidates for dark matter are particles called weakly interacting massive particles, or WIMPs. These would be particles that have mass and therefore gravity, but don't interact electromagnetically, meaning they don't emit, absorb or reflect light. They would pass through ordinary matter almost entirely without interaction. Experiments in deep underground laboratories, shielded from cosmic ray backgrounds, have been searching for WIMPs for decades using detectors made of various materials sensitive to the slight recoil when a WIMP strikes an atomic nucleus. The detectors have become extraordinarily sensitive. So far, no definitive detection. The parameter space where WIMPs could hide has been progressively narrowed. WIMPs might still be out there, just lighter or more weakly interacting than expected, or they might not exist at all. Other dark matter candidates have attracted increasing attention as the WIMP searches have come up empty. Axions are extremely light particles originally proposed in the 1970s to solve a different problem in particle physics related to why the strong nuclear force doesn't violate a symmetry called CP symmetry. Axions would be incredibly light, perhaps a billion times lighter than a proton, and would interact with photons in the presence of strong magnetic fields. Several experiments are specifically searching for axions by looking for photons produced when axions pass through powerful magnetic fields. The ADMX experiment and others have begun probing the relevant parameter space. Sterile neutrinos are hypothetical heavy cousins of ordinary neutrinos that don't interact through the weak nuclear force. They could have been produced in the early universe and would behave as dark matter today. They might betray their presence by decaying slowly into ordinary photons and neutrinos, producing a narrow X-ray line from the centers of galaxies and clusters. In 2014, an unidentified X-ray line at 5 kilo-electron-volts was detected in X-ray observations of galaxy clusters and the Andromeda galaxy. Some researchers interpreted this as the decay signature of a 7 kilo-electron-volt sterile neutrino. The interpretation remains contested. More sensitive X-ray telescopes will test it. Dark energy is even more mysterious than dark matter because it requires something genuinely new in physics. Not just a new particle, but a new type of energy with properties unlike anything we've ever encountered. The discovery of dark energy came as a complete shock in 1998, When two independent teams were using observations of Type Ia supernovae to measure how the universe's expansion rate had changed over time. Type Ia supernovae are explosions of white dwarf stars that happen to have nearly the same intrinsic brightness every time, making them excellent standard candles for measuring cosmic distances. By comparing how bright they appear to their actual brightness, you can measure their distance. By measuring the redshift of their host galaxies, you can measure how fast those galaxies are receding. Combining distance and velocity for supernovae at different distances gives you the history of the universe's expansion rate over cosmic time. Both teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory and one by Brian Schmidt and Adam Rias, expected to find that gravity was slowing the expansion down over time. Instead, they found that distant supernovae were fainter than expected, meaning they were farther away than the models predicted. The expansion wasn't slowing down, it was speeding up. Something was pushing galaxies apart faster and faster as time went on, counteracting gravity on the largest scales. That something was dark energy. Perlmutter, Schmidt and Rias shared the 2011 Nobel Prize in Physics for this discovery. The finding forced cosmologists to bring back Einstein's cosmological constant. Einstein had added it to his equations to keep the universe static and then removed it when Hubble showed the universe was expanding. It turns out the cosmological constant doesn't make the universe static, but it does cause it to accelerate. Einstein had introduced it for the wrong reasons and then abandoned it also for wrong reasons. In a remarkable irony of physics history, his discarded constant turned out to be the dominant component of the universe. Nobody knows what dark energy physically is at a fundamental level. The cosmological constant interpretation treats it as an energy inherent to empty space itself, a vacuum energy that exists even in the absence of any matter or radiation. Quantum field theory predicts that empty space should indeed have energy because of quantum fluctuations, but the predicted value from quantum field theory is about 120 orders of magnitude larger than the observed value of dark energy. This mismatch is called the worst prediction in the history of physics, and it's a genuine crisis for fundamental theory. The observed dark energy is almost zero, but not quite zero, and understanding why it has this particular tiny value is one of the deepest unsolved problems in physics. Alternative explanations for dark energy involve dynamical fields called quintessence that vary in space and time rather than being a fixed constant. If dark energy is quintessence, its value today would differ from its value in the past, and precise measurements of the expansion history could detect this evolution. So far, observations are consistent with a cosmological constant that doesn't change, but the measurements aren't precise enough to definitively rule out slow evolution. Future surveys like the Euclid satellite and the Vera Rubin Observatory's Legacy Survey of Space and Time are specifically designed to measure whether dark energy evolves with time. Finding evolution would be revolutionary, pointing toward a dynamic field rather than a vacuum constant. The cosmic microwave background maps from Planck and WMAP revealed not just the composition of the universe, but an extraordinarily detailed picture of the acoustic physics in the early universe. The pattern of hot and cold spots in the microwave background encodes the density variations in the early universe. Different angular scales in the pattern correspond to different physical sizes of structures. The pattern has a characteristic series of peaks and troughs called acoustic peaks that arise from sound waves that propagated through the hot plasma of the early universe before the universe became transparent at 380,000 years. It was a tightly coupled plasma where photons, protons and electrons all interacted strongly. Regions of slightly higher density attracted more material through gravity, compressing the plasma and raising its pressure. The increased pressure then pushed the plasma back outward. This created acoustic oscillations, pressure waves bouncing back and forth in the plasma like sound waves in air. These waves oscillated for the entire first 380,000 years until the universe cooled enough for electrons to combine with protons into neutral hydrogen atoms. At that moment, the coupling between photons and matter ended abruptly. The oscillations froze in place and the photons streamed freely across space. The pattern of peaks and troughs in the cosmic microwave background is a snapshot of where all those acoustic waves were at the precise moment they froze. The positions and heights of these acoustic peaks are extraordinarily informative. The position of the first peak tells us the geometry of the universe, confirming it's flat to within measurement precision. The relative heights of different peaks tell us the ratio of ordinary matter to dark matter. The precise shape of the spectrum tests inflation models. A universe with more ordinary matter has acoustic peaks at different positions than one with less. A universe with more dark matter damps the oscillations differently. The cosmic microwave background is like a precision instrument that the early universe itself built and left for us to read. By reading it carefully, we can measure the properties of the universe to remarkable accuracy. The acoustic oscillations left their mark not just in the cosmic microwave background, but also in the distribution of galaxies we see today. Those same sound waves that oscillated in the early plasma established a preferred scale, the distance that sound could travel before the plasma became transparent. Today, that scale shows up as a slight excess of galaxy pairs separated by a particular distance, about 500 million light-years. This feature, called baryon acoustic oscillations, provides a standard ruler for measuring cosmic distances. By measuring how the apparent size of this ruler changes with redshift, cosmologists can map the expansion history of the universe and constrain dark energy. Baryon acoustic oscillations have been measured in multiple galaxy surveys, including the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. They provide constraints on dark energy that are completely independent of supernova measurements. And the two methods agree with each other, providing strong mutual confirmation of the standard cosmological model. The consistency between completely different measurement techniques, all giving the same answer, is one of the most compelling arguments that the standard cosmological model captures something true about the universe. The large-scale structure of the universe, the cosmic web of galaxy filaments, sheets and voids, provides yet another powerful probe of the Big Bang cosmology and its aftermath. Gravity amplified the tiny density variations from inflation over billions of years, growing them into the structures we see today. The pattern of this large-scale structure depends sensitively on the amount and type of matter in the universe, the expansion history, and the initial conditions set by inflation. Computer simulations that start with the initial conditions measured from the cosmic microwave background and evolve them forward using known physics produce a cosmic web that matches observations of the actual universe in remarkable detail. Massive galaxy surveys have mapped the three-dimensional distribution of millions and eventually billions of galaxies across enormous volumes of space. The Sloan Digital Sky Survey mapped over 1 million galaxies in a large fraction of the sky visible from New Mexico. The 2DF Galaxy Redshift Survey in Australia mapped hundreds of thousands of galaxies from the southern hemisphere. The resulting maps revealed the cosmic web in exquisite detail, filaments of galaxies stretching across hundreds of millions of light years, walls of galaxies at the intersections of filaments. Between them, vast cosmic voids nearly empty of galaxies, some spanning hundreds of millions of light years. The whole structure resembles an enormous three-dimensional soap bubble lattice, with galaxies concentrated on the surfaces and intersections of the bubbles. The agreement between these observed maps and simulations of structure formation in a universe with cold dark matter and a cosmological constant is one of the triumphs of modern cosmology. The simulations, run on some of the world's most powerful supercomputers, can reproduce the main features of the cosmic web from the initial conditions measured in the microwave background. The fact that the same physical model, with the same parameters, fits both the microwave background from 380,000 years after the Big Bang and the galaxy distribution today, billions of years later, is a powerful confirmation that we understand the broad outlines of cosmic history. One of the most important and troubling puzzles in modern cosmology is the Hubble tension. The Hubble constant describes the current rate of expansion of the universe, how fast galaxies are receding from us per unit of distance. Measuring it precisely is critical because it sets the age and size of the observable universe and constrains all other cosmological parameters. The tension arises because two different methods of measuring the Hubble constant give significantly different answers, and the discrepancy has grown more statistically significant as both measurements have improved. One method measures the Hubble constant in the local universe by building a cosmic distance ladder. You start with nearby stars whose distances can be measured geometrically using the tiny shift in apparent position as Earth orbits the Sun. You then use those stars to calibrate Cepheid variable stars in slightly more distant galaxies. You use Cepheids to calibrate the brightness of Type Ia supernovae. You then measure the recession velocities of galaxies hosting those supernovae and compare them to the supernova distances. Adam Rias and colleagues have refined this measurement for decades, and it currently gives a Hubble constant of about 73 kilometers per second per megaparsec, meaning a galaxy 1 megaparsec away is receding at 73 kilometers per second, 2 megaparsecs away is receding at 146 kilometers per second, and so on. The second method extracts the Hubble constant from the cosmic microwave background by fitting the entire standard cosmological model to the detailed pattern of temperature fluctuations measured by Planck. This gives a value of about 67 kilometers per second per megaparsec. The difference between 67 and 73 might sound small, but it's now a 5 sigma discrepancy, a statistical gap that in physics represents overwhelming evidence that the difference is real and not due to random measurement error. If both measurements are correct, something in our standard cosmological model is wrong. The James Webb Space Telescope has been used to check the Cepheid calibrations independently, examining Cepheids in galaxies that are also hosts of Type Ia supernovae. The results confirmed Rias's measurements rather than pointing to a systematic error in the distance ladder. This makes it harder to dismiss the Hubble tension as a simple calibration error. Some new physics may be required. The proposals for resolving the Hubble tension are numerous and creative. Early dark energy suggests that dark energy was much stronger in the early universe and has since diluted, changing the sound horizon scale that the microwave background method relies on. If the sound horizon is smaller than assumed, the inferred Hubble constant from the microwave background increases toward the local measurement. But introducing early dark energy tends to worsen agreement with other observations like galaxy clustering, so it's not a clean solution. Modified gravity theories suggest that gravity behaves differently on cosmic scales than Einstein's equations predict, changing the expansion history. Interacting dark matter and dark energy models allow the dark components to exchange energy, modifying the expansion. None of these solutions has been compellingly confirmed. The Hubble tension might be telling us about new physics beyond the standard cosmological model, potentially the most important clue we have for what lies beyond it. Or it might eventually resolve through a subtle systematic error in one of the measurement chains. The current state of affairs is genuinely uncertain, and the answer could go either way. The neutrino's role in Big Bang cosmology is important and often underappreciated by the general public. Neutrinos are the second most abundant particles in the universe after photons. There are about 300 neutrinos per cubic centimeter of space everywhere in the universe, a relic of the Big Bang just as the microwave background photons are. These cosmic background neutrinos were last in thermal contact with other matter when the universe was about 1 second old, far earlier than the microwave background photons decoupled at 380,000 years. The cosmic neutrino background is in principle even more ancient than the microwave background, but detecting it directly is currently impossible because the neutrinos have such low energies. Neutrinos have important indirect effects on cosmology that can be measured through their influence on other observables. In the early universe, neutrinos contributed to the total energy density alongside photons and affected the expansion rate during primordial nucleosynthesis. The number of neutrino species affects the expansion rate, which in turn affects how much helium was produced. Measurements of the cosmic helium abundance agree with 3 neutrino species consistent with the standard model of particle physics and providing cosmological confirmation of the particle physics result. The masses of neutrinos affect the growth of large-scale structure in the universe. Neutrinos are very light but not massless, as demonstrated by laboratory experiments showing that different types of neutrinos transform into each other, which can only happen if they have mass. Massive neutrinos move fast enough in the early universe to smooth out density fluctuations on small scales, suppressing the growth of small structures. The amount of suppression depends on the total neutrino mass. By measuring the pattern of structure in galaxy surveys and in the cosmic microwave background, cosmologists can constrain the sum of neutrino masses. Current cosmological data limit the sum of all three neutrino masses to less than about 0.12 electron volts, a tighter constraint than any direct laboratory measurement has achieved. This is one of the most striking examples of cosmology as a tool for particle physics. The largest structures in the universe, the cosmic web of galaxies, are sensitive to the masses of the lightest known massive particles. As galaxy surveys become more powerful, the cosmological constraint on neutrino masses will tighten further, potentially measuring the actual values rather than just upper limits. Future surveys like the Euclid satellite and the Vera Rubin Observatory could measure the neutrino mass sum to better than 0.02 electron volts, providing a determination of a particle physics quantity from astronomical observations. Primordial nucleosynthesis, the forging of the light elements in the first 3 minutes, deserves a deeper look because it's one of the most precisely tested predictions in all of cosmology. When the universe was between about 1 second and 3 minutes old, it was hot enough and dense enough for nuclear reactions to proceed. Protons and neutrons combined to form deuterium nuclei, two particles bound together. Deuterium nuclei combined to form helium-3 and helium-4. Some helium-4 combined with deuterium to make lithium-7. Then the universe cooled below the threshold for nuclear reactions, and the composition froze. The predicted abundances from these calculations depend on just one parameter, not fixed by the microwave background, the density of ordinary matter relative to photons in the early universe. Given that density, the predictions for the helium, deuterium, helium-3 and lithium abundances are definite numbers that can be compared to observations of the oldest, most chemically unprocessed material in the universe. The helium abundance has been measured in low metallicity regions of dwarf galaxies where little stellar processing has occurred. The result, about 25% helium by mass, matches the Big Bang prediction to within measurement uncertainties. The deuterium abundance has been measured in ancient gas clouds that lie in front of distant quasars, absorbing specific wavelengths of the quasar's light. Several such systems have been measured, and they consistently give a deuterium abundance that agrees with the Big Bang nucleosynthesis calculation. These agreements across completely independent measurements of completely different elements provide compelling evidence that we correctly understand the physics of the universe when it was only a few minutes old. The one persistent discrepancy is the lithium problem. The Big Bang prediction for lithium-7 is about 3 times higher than what is observed in the oldest, most metal-poor stars in our galaxy. This discrepancy has been known for decades and has not gone away as measurements have improved. The most likely explanation is that these ancient stars have processed some of their primordial lithium through nuclear reactions in their interiors over billions of years, depleting the surface abundance. Some stellar models predict this, but demonstrating it definitively has proven difficult. The lithium problem remains an unresolved tension in Big Bang cosmology, though most cosmologists regard it as a problem of stellar physics rather than a fundamental challenge to the Big Bang. The epoch of reionization is a frontier in Big Bang cosmology that has seen rapid observational progress in recent years. After the cosmic microwave background was released at 380, Thousand years, the universe entered the cosmic dark ages. There were no stars, no galaxies, no sources of light. The universe was filled with a fog of neutral hydrogen gas that slowly cooled as the universe expanded. The first stars began forming perhaps 200 million years after the Big Bang, when gravity had amplified the density fluctuations enough to collapse the first clouds of gas. These first stars, called population 3 stars, were very different from stars today. The gas available to form them was almost pure hydrogen and helium, with no heavy elements. Without heavy elements, the cooling processes that regulate star formation worked differently. The first stars are thought to have been predominantly very massive, perhaps hundreds of times the mass of the Sun. They burned brilliantly but briefly, living only a few million years before exploding as supernovae. Their explosions seeded the surrounding gas with the first heavy elements and also produced the first black holes. The ultraviolet radiation from the first stars began ionizing the surrounding neutral hydrogen, creating bubbles of ionized gas around each star-forming region. As more stars formed, the bubbles grew and eventually began overlapping. By about 1 billion years after the Big Bang, the entire intergalactic medium had been reionized. The universe had emerged from the cosmic dark ages and entered the era of galaxies, stars, and increasingly heavy element chemistry that continues today. Observing the epoch of reionization is challenging because it's so distant and because neutral hydrogen absorbs certain wavelengths of light efficiently, making it hard to see through. But the James Webb Space Telescope has revolutionized this field by detecting individual galaxies from the reionization epoch and characterizing their properties. The telescope has found galaxies from when the universe was only a few 100 million years old, revealing the earliest known star-forming systems. What James Webb has found has been somewhat surprising. The early universe appears to contain more massive and more luminous galaxies than our models predicted for those early times. Some galaxies seen when the universe was only 500 to 800 million years old look as massive and structurally evolved as galaxies in the much later universe. They shouldn't be that big that fast, according to standard models of galaxy formation, which predict that galaxies grow gradually through mergers and accretion over billions of years. Several explanations are being debated. The initial mass function of stars in the early universe might have been skewed toward more massive, more luminous stars, producing more light per unit of stellar mass. Star formation efficiency might have been higher in the early universe because the gas was denser and less enriched with heavy elements that suppress star formation. Dark matter halos might have assembled more rapidly than expected in the early universe, or there might be physics missing from our models entirely. The James Webb observations have created a productive crisis in models of early galaxy formation. The 21-centimeter cosmology is one of the most exciting frontiers in observational cosmology. Neutral hydrogen emits and absorbs radio waves at a wavelength of 21 centimeters due to a quantum mechanical transition involving the spin states of the electron in a hydrogen atom. Before reionization, the universe was full of neutral hydrogen. By observing the 21 centimeter signal at different radio frequencies, corresponding to different redshifts, and therefore different distances and cosmic times, you can map the three-dimensional distribution of neutral hydrogen through the Dark Ages and the reionization epoch. In principle, this would give us a three-dimensional movie of reionization, showing how the ionized bubbles grew and merged. In practice, this is enormously difficult because radio interference from terrestrial sources is overwhelming. Satellites, cellular networks, and other radio emitters produce signals that dwarf the cosmological signal. Radio telescopes for 21-centimeter cosmology must be built in remote radio-quiet locations and use sophisticated techniques to separate the faint cosmological signal from the overwhelming foreground. In 2018, the EDGES experiment, a simple antenna in the Western Australian desert, reported a detection of the 21-centimeter signal from the cosmic dawn, the period when the first stars were beginning to heat the surrounding gas. The signal appeared at a redshift corresponding to about 180 million years after the Big Bang. But the signal was twice as strong as the maximum expected from standard models. This could indicate that the early universe was cooler than expected, perhaps because dark matter was absorbing energy from the ordinary matter at that epoch. Dark matter interactions with ordinary baryonic matter in the early universe could cool the gas, making the 21-centimeter absorption feature stronger. If confirmed, this would be the first indication of interactions between dark matter and ordinary matter beyond gravity. The result remains controversial, and independent experiments have not yet confirmed it. The hydrogen epoch of reionization array in South Africa and the square kilometre array being built in Australia and South Africa are designed to detect and map the 21-centimeter signal in detail. The square kilometre array in particular will have extraordinary sensitivity and should definitively detect the epoch of reionization signal, mapping how the universe was reionized bubble by bubble. The question of what happened before the Big Bang, or at the Big Bang itself, is where cosmology meets quantum gravity and philosophy. The standard Big Bang model breaks down at the very beginning. At the Planck time, about 10 to the negative 43 seconds after the beginning, the universe was so small and so dense that quantum gravity effects were as important as the ordinary physics of matter and radiation. We don't have a complete theory of quantum gravity, so we can't reliably describe the universe at those earliest instants. Several theoretical frameworks offer different pictures. Loop quantum cosmology, which applies the ideas of loop quantum gravity to the universe as a whole, predicts that quantum effects halt the classical gravitational collapse before a singularity forms and cause a bounce. In this picture, our universe expanded from a previous contracting universe. The Big Bang was not a true beginning, but a transition point. Loop quantum cosmology makes specific predictions about the spectrum of primordial fluctuations that differ slightly from standard inflation predictions, and that future cosmic microwave background measurements might be sensitive to. String gas cosmology suggests that the universe began as a hot, dense gas of strings in a high-temperature equilibrium state rather than a singular point. In this framework, the universe initially had more than 3 large spatial dimensions, and the dynamics of string interactions preferentially chose 3 of them to expand into the large dimensions we observe, while the others remain small and compact. This provides an alternative mechanism for setting the initial conditions of the Big Bang without invoking a singular beginning. The no-boundary proposal by Hawking and Hartle treats the universe as a closed quantum mechanical system with a specific quantum state that has no boundary in time. In their framework, time itself emerged from a more fundamental dimension as the universe emerged from a quantum state. There is no moment of creation and no prior state. The question of what happened before the Big Bang doesn't arise because the concept of before doesn't apply. Time is a feature of the universe, not something the universe exists within. The multiverse is a concept that emerges naturally from eternal inflation and has profound implications. Most inflationary models predict that inflation didn't happen just once and uniformly everywhere. The inflaton field, the hypothetical quantum field driving inflation, fluctuates quantum mechanically. In some regions, the fluctuations cause inflation to end and normal Big Bang evolution to begin, producing a universe like ours. In other regions, the fluctuations sustain or even amplify the inflation. These inflating regions expand exponentially while new bubbles of non-inflating space form continuously. The result is an enormous or possibly infinite collection of separate universes, each potentially with different physical constants, different amounts of dark energy, different particle masses. This eternal inflation scenario implies that our observable universe is just one bubble in a vast multiverse. The physical constants we observe might be accidental features of our particular bubble rather than uniquely determined values. The smallness of dark energy, which is one of the most mysterious fine-tuning problems in physics, might be explained anthropically. Among all the bubbles in the multiverse, only those with a small enough dark energy allow galaxies to form and complex structures to exist. Observers like us inevitably find ourselves in bubbles where the conditions permit our existence. This is the anthropic argument, and it generates strong reactions among physicists. Some find it compelling as the only available explanation for seemingly fine-tuned constants. Others find it deeply unsatisfying because it seems to abandon the project of explaining why the universe has the properties it does. If the answer is simply that we had to find ourselves in a universe compatible with our existence, then we've stopped doing physics and started doing philosophy. The debate about the multiverse and the anthropic principle touches on fundamental questions about what science is and what counts as an explanation. One potentially observable signature of the multiverse would be the collision of our bubble with neighboring bubbles. If another bubble universe formed near ours and its wall collided with our bubble's wall, the collision would leave a characteristic imprint in the cosmic microwave background. The imprint would appear as a circular region of the sky with anomalous temperature properties. Searches have been conducted in WMAP and Planck data for such circular anomalies. Some candidate regions have been identified and analyzed. None has been confirmed as a bubble collision signature. The search continues as microwave background measurements improve. The question of dark matter's nature is being pursued on multiple fronts simultaneously. Underground direct detection experiments have become extraordinarily sensitive. The Lux Zeppelin experiment in the Homestake mine in South Dakota, shielded from cosmic rays by a mile of rock above it, has achieved sensitivity to WIMP interactions that would be 100 times smaller than a hydrogen nucleus cross-section. It's found nothing. placing limits on WIMP interactions that rule out much of the parameter space that theorists considered well motivated. If WIMPs exist, they're increasingly constrained to specific regions of parameter space. Indirect detection experiments search for signals of dark matter annihilating with itself in regions of high dark matter density, like the galactic center. If dark matter is made of WIMPs, two WIMPs meeting in the galactic center could annihilate into gamma rays, antimatter, or neutrinos. The Fermi Gamma Ray Space Telescope has been monitoring the galactic center for years, looking for such signals. There are tantalizing excesses in the data that some researchers have interpreted as dark matter annihilation signals, but conventional astrophysical sources can also explain them, and the interpretations remain contested. Collider searches for dark matter at particle accelerators have also come up empty so far. At the Large Hadron Collider, high-energy proton collisions might produce dark matter particles that escape the detector invisibly, showing up as missing energy and momentum. Despite extensive searches at the highest energies yet achieved, no dark matter particles have been found. The null results from colliders, underground detectors, and telescopes have collectively pushed dark matter models into increasingly constrained corners, but they haven't ruled out all possibilities. The possibility that dark matter is not a particle at all, but something else entirely, is gaining attention. Modified gravity theories attempt to explain the observations usually attributed to dark matter by modifying Newton's law of gravity or Einstein's general relativity in the regime of very low accelerations. Modify Newtonian dynamics, proposed by Mordecai Milgrom in 1983, replaces Newton's second law in a specific way in the limit of very low accelerations and can reproduce galaxy rotation curves without dark matter. However, it has serious difficulties explaining the dynamics of galaxy clusters, the acoustic peaks in the cosmic microwave background, and the detailed structure of the cosmic web, all of which are naturally explained by dark matter, but poorly reproduced by modified gravity alone. Most cosmologists consider modified gravity an incomplete alternative rather than a full solution. The baryon asymmetry problem, why there's matter rather than an equal mixture of matter and antimatter, connects cosmology directly to particle physics in an important way. In the very early universe, matter and antimatter were created in equal quantities from pure energy through pair production. As the universe cooled below the energy threshold for creating each type of particle, those particles and their antiparticles annihilated each other, converting their mass back into photons. For ordinary protons and electrons, this happened when the universe was about 1 microsecond old. At that point, for every billion matter-antimatter pairs that annihilated, there was one extra matter particle left over. That 1 in a billion excess is all the ordinary matter in the universe today. Where did that excess come from? This is the baryogenesis problem. Andrei Sakharov identified in 1967 the 3 conditions necessary for matter-antimatter asymmetry to develop from a symmetric beginning. Processes that change the number of baryons must exist. Physics must distinguish matter from antimatter in its interactions, called CP violation. And these processes must have occurred when the universe was out of thermal equilibrium. All 3 conditions are present in principle in the standard model of particle physics, but the amount of CP violation in the standard model is far too small to explain the observed asymmetry by many orders of magnitude. New physics is needed. Several mechanisms for generating the baryon asymmetry have been proposed. Electroweak baryogenesis suggests that the asymmetry was generated during the electroweak phase transition, when the Higgs field acquired its current value and the universe went from a symmetric high-temperature phase to the broken symmetry low-temperature phase we inhabit. At the boundary between the two phases, where bubbles of the new phase expanded into the old, certain processes could generate a slight matter excess. However, making electroweak baryogenesis work quantitatively requires new particles beyond the standard model that haven't been found yet at the Large Hadron Collider. Leptogenesis generates the asymmetry first in the lepton sector, involving neutrinos and electrons, and then converts it to baryon asymmetry through processes that are active at high temperatures. Heavy versions of neutrinos, called right-handed neutrinos, could have been produced in the early universe and decayed with a slight preference for matter over antimatter. This is particularly attractive because it connects the baryon asymmetry to the small masses of ordinary neutrinos through a mechanism called the seesaw mechanism. Unfortunately, leptogenesis is very difficult to test experimentally because the relevant right-handed neutrinos would be extremely heavy, far beyond the reach of current accelerators. Future experiments measuring CP violation in neutrino oscillations, the transformation of one type of neutrino into another, will test whether neutrinos violate matter-antimatter symmetry to the degree required for leptogenesis. The deep underground neutrino experiment in the United States and the Hyperkamiokande experiment in Japan are both designed to measure neutrino CP violation with high precision. Finding a large CP asymmetry in neutrinos would be strong indirect evidence for leptogenesis. Gravitational waves from the Big Bang era provide another window into early universe physics that is entirely independent of electromagnetic observations. Just as inflation is predicted to have produced primordial gravitational waves that left a swirling polarization pattern in the cosmic microwave background, various other processes in the early universe are predicted to have produced gravitational waves of different frequencies and amplitudes. Phase transitions in the early universe, where the universe changed from one state to another as it cooled, could have produced gravitational waves through the collision and merger of bubbles of the new phase. If the electroweak phase transition was strongly first order, it would have produced a gravitational wave background peaking at frequencies observable by LISA, the planned space-based gravitational wave detector. Cosmic strings are another hypothetical source of primordial gravitational waves. Cosmic strings would be topological defects, one-dimensional objects of enormous mass per unit length, formed when certain types of symmetry were broken in the early universe as it cooled through phase transitions. Infinite networks of cosmic strings would oscillate and emit gravitational waves continuously. The cumulative signal from a network of cosmic strings throughout cosmic history would form a stochastic gravitational wave background spanning a wide range of frequencies. Pulsar timing arrays might already be detecting this background, or it might be distinguishable from the supermassive black hole merger background with future experiments. The precision of modern cosmological measurements has enabled tests of inflation that would have seemed impossible 20 years ago. Different inflationary models predict slightly different shapes for the spectrum of primordial fluctuations and different amplitudes for the primordial gravitational wave background. Current measurements of the microwave background and large-scale structure already rule out the simplest inflationary models and constrain the viable models to a relatively narrow class. Models that produce too many large fluctuations on small scales are ruled out by microwave background measurements. Models that produce too many primordial gravitational waves are constrained by the absence of the swirling polarization pattern. The inflationary models that remain viable after these constraints tend to predict a specific relationship between the amplitude of primordial gravitational waves and the deviation of the fluctuation spectrum from perfect scale invariance. Future experiments measuring the microwave background polarization with higher sensitivity will be able to test this relationship. The Simons Observatory, currently being built in the Atacama Desert in Chile, will dramatically improve sensitivity to the primordial gravitational wave signal. CMB-S4, a larger planned experiment, will push the limits further. If primordial gravitational waves are detected, it will confirm inflation and specify which class of inflationary model is correct. The Sunyaev-Zeldovich effect is a powerful tool for finding galaxy clusters at large distances and testing cosmological models. When cosmic microwave background photons pass through the hot gas filling a galaxy cluster, some of them scatter off the electrons in the gas and gain energy. This changes the spectrum of the microwave background in the direction of the cluster, creating a distinctive pattern of slightly decreased intensity at some wavelengths and increased intensity at others. The size of the effect is proportional to the total amount of hot gas in the cluster, but is independent of the cluster's distance. Unlike most astronomical brightness measurements, which depend strongly on distance, this makes the Sunyaev-Zeldovich effect particularly valuable for finding distant galaxy clusters in microwave background maps. The South Pole Telescope and the Atacama Cosmology Telescope have found hundreds of galaxy clusters out to high redshifts using this technique. The number and distribution of galaxy clusters as a function of redshift is a sensitive probe of cosmology. More clusters form earlier in a universe with more matter. The rate at which clusters grow depends on the nature of dark energy. The cluster counts from microwave background surveys are now competitive with other cosmological probes and provide independent constraints on the matter density and dark energy. The cosmic microwave background polarization contains more information than the temperature alone and is currently being measured with increasing precision. The polarization can be decomposed into two types called E modes and B modes after their mathematical properties, analogous to the distinction between electric and magnetic fields. E-mode polarization is produced by the acoustic oscillations in the early universe plasma and has been measured in detail by Planck and ground-based experiments. B-mode polarization on large angular scales can only be produced by primordial gravitational waves from inflation or by the conversion of E modes to B modes through gravitational lensing on small angular scales. The lensing B modes have been measured and provide information about the distribution of matter, along the line of sight, complementing other lensing measurements. The primordial B modes from inflation remain below current detection limits. Current experiments place limits on the ratio of gravitational wave amplitude to density fluctuation amplitude, called the tensor-to-scalar ratio, of less than about 0.036. Many inflationary models predict values well below this limit, which is why the search has not yet succeeded. Future experiments will push sensitivity to tensor-to-scalar ratios below 0.001, covering most of the theoretically motivated range. The S8 tension, a discrepancy between the amount of matter clustering in the universe as measured by different methods, is a persistent puzzle alongside the Hubble tension. The Planck microwave background data predicts that matter in the universe should be clustered to a certain degree today, characterized by a parameter called S8 that combines the matter density and the amplitude of fluctuations. But surveys of weak gravitational lensing, which measure how the gravitational pull of matter distorts the shapes of background galaxies, consistently find less clustering than Planck predicts, with a discrepancy of about 2 to 3 sigma. If the S8 tension is real rather than a systematic measurement error, it might indicate that dark matter has properties beyond those of perfectly cold and collisionless particles. Self-interacting dark matter, where dark matter particles scatter off each other through some force beyond gravity, could smooth out dark matter on small scales and reduce the clustering compared to cold dark matter. Warm dark matter, with particles moving fast enough to erase small-scale structure, could also reduce clustering. Or the tension might reflect some additional physics in the late universe that affects how matter clusters, such as interactions between dark matter and dark energy. Current data don't definitively resolve the tension, and it remains an active area of research. The future of Big Bang cosmology research is extraordinarily rich. The Euclid satellite, launched in 2023, will survey the distribution of approximately 2 billion galaxies over more than a third of the sky out to high redshifts. By measuring both the galaxy clustering pattern and the weak gravitational lensing of galaxy shapes, it will constrain dark energy and dark matter with unprecedented precision. The Vera Rubin Observatory's legacy survey of space and time will complement Euclid by repeatedly imaging billions of objects across the southern sky, measuring Type Ia supernovae distances, detecting transient events, and building a deep galaxy catalogue with exquisite photometry. The Nancy Grace Roman Space Telescope will survey large areas of sky from space with the resolution of the Hubble Space Telescope, enabling measurements of both supernova distances and weak gravitational lensing that are free of atmospheric distortions. Together, these next-generation surveys will produce cosmological measurements with dramatically reduced uncertainties, either confirming the standard model to higher precision or revealing the new physics hiding in the Hubble tension, the S8 tension, or elsewhere. The Square Kilometre Array will revolutionize radio astronomy across an enormous range of science, including cosmology. By mapping neutral hydrogen across billions of light years using the 21 centimeter line, it will produce three-dimensional maps of the large structure of the universe that complement optical and infrared galaxy surveys. It will also search for the epoch of reionization signal, attempt to detect primordial gravitational waves through their effects on pulsars, and search for additional sources of gravitational waves through pulsar timing. The next generation cosmic microwave background experiments, particularly CMBS-4, will push microwave background science to its limits. By deploying arrays of hundreds of thousands of detectors at telescope sites in Chile and the South Pole, CMBS-4 will achieve noise levels roughly 30 times lower than Planck in some configurations. This will enable measurements of the primordial gravitational wave background to tensor-to-scalar ratios below 0.001, measurements of the neutrino mass sum at the level of 0.014 electron volts, potentially measuring individual neutrino masses, and detailed maps of the lensing of the microwave background that can constrain the growth of structure in the universe to high precision. Looking back across a century of Big Bang cosmology, the progress is almost incomprehensible in its scope. In 1915, we didn't know other galaxies existed. In 1929, we discovered the universe was expanding. In the 1940s, the theory of primordial nucleosynthesis was developed. In 1965, the cosmic microwave background was accidentally discovered by engineers cleaning a telescope antenna. In 1980, inflation was proposed to explain the horizon and flatness problems. In 1992, the temperature fluctuations in the microwave background were first mapped by COBE. In 1998, dark energy was discovered through supernova observations. In 2003, WMAP produced the first precision map of the microwave background. In 2013, Planck refined that map to extraordinary precision. In 2023, Euclid launched to map billions of galaxies. At each step, the universe revealed something new and surprising. The steady-state theory was overturned. Dark matter was discovered through its gravitational effects. Dark energy appeared unexpectedly in the supernova data. Inflation was confirmed by the scale-invariant fluctuation spectrum. The universe turned out to be 13.8 billion years old, flat, and mostly made of things we don't understand. The pattern of each decade's surprises suggests the next century will bring equally transformative discoveries. What we can say with confidence after a century of research is that the Big Bang model is fundamentally correct. The universe began in a hot, dense state approximately 8 billion years ago. It expanded and cooled. Light elements formed in the first few minutes. The first atoms formed at 380,000 years, releasing the cosmic microwave background. Gravity amplified initial density fluctuations into the cosmic web of galaxies. Stars formed, burned and exploded, seeding space with heavy elements. Later generations of stars formed planetary systems from enriched gas. On at least one of those planets, chemistry became biology, became consciousness, became telescopes pointed at the universe that created them. The Big Bang is not just a theory about the past. It's a framework that connects particle physics, nuclear physics, thermodynamics, gravity, and quantum mechanics in a coherent story of cosmic evolution. Every piece of that story has been tested observationally and found to be consistent. The standard cosmological model that emerged from a century of work is one of the greatest achievements of human science. But the story is not finished. The nature of dark matter and dark energy remain unknown. The mechanism of inflation is unconfirmed. The origin of the matter-antimatter asymmetry is unsolved. The physics of the very first moments is beyond current theory. The Hubble tension might be pointing toward new physics. The unexpected galaxies found by James Webb might require modifications to our models of structure formation. The answers to these questions will require new observations, new theoretical frameworks, and perhaps entirely new ways of thinking about space, time, and matter. The universe began with a bang that we can now characterize with extraordinary precision. It has been expanding and evolving for nearly 14 billion years. We are among its most complex recent products, made of atoms forged in stellar furnaces, standing on a planet circling an ordinary star in one of several 100 billion galaxies, looking back at the light from the first transparent moment and slowly working out how everything began. That is the project of Big Bang cosmology, and after 100 years, it is still the most ambitious and rewarding investigation in the history of human curiosity.